Now take a moment and practice with these definitions. Let's say you have the set of real numbers, and we define the relation R on the set of real numbers as A is related to B if and only if A is less than or equal to B. So what you want to do is use these definitions and check whether this relation R is reflexive, irreflexive, symmetric, antisymmetric, or transitive. And one more example for you to work through is this one. We have the set of non-zero real numbers, remember that's what the star means, which is defined as A is related to B by this relation S if and only if A times B is positive. That was another way of saying that A and B have the same sign. Remember we talked about that relation previously. So again, use these definitions, practice with them to determine whether or not this relation S has these properties. Let's look at some more examples. And we'll keep these definitions as handy references. Let's say we have a relation T defined on the set of positive real numbers given by A is related to B if and only if A over B is rational. So one thing you can think of is if I have 4 pi over 3 pi, well, that's rational because the pi's will cancel. I'll have 4 over 3. I'll have integer over integer. So that will be rational, even though 4 pi and 3 pi individually are not rational. So let's see. A over A for any non-zero real number is going to give you 1, and 1 is a rational number. So what that tells you is the relation T is reflexive. And remember, reflexive and irreflexive are mutually exclusive from each other. So that tells us T is not irreflexive. What about symmetric? Well, if A over B can be written as M over N, remember, everything is non-zero here. Hopefully you remember that discussion from some time ago about worrying whether the numerator or the denominator is 0 when you're flipping a fraction. We don't have that concern here because we're assuming everything we're working with is non-zero. So if you have A over B, which is real number over real number, and you can write it as M over N, in other words, we're thinking that A over B is the 4 pi over 3 pi, and the M over N is the 4 over 3 that's equivalent in value to it. Then the reciprocal B over A is also going to be rational because B over A is N over M, and both of these are non-zero integers, so we're all good. Another creative example is root 2 and root 18. So think for a moment about root 2 and root 18. If I do root 2 over root 18, well, I can simplify root 18 as 3 root 2, and then the common factor of square root of 2 is eliminated, which means we have 1/3, which is rational. And if we flipped it over, the same thing would be true. Okay? However, this is actually going to tell us that this is not anti-symmetric because A is related to B and B is related to A, but that does not imply that A equals B. So in other words, T is not anti-symmetric. Just to give you a quick example of something that is anti-symmetric, the simplest example of anti-symmetric is the equals relation. A equals B and B equals A definitely implies that A equals B. So equals, so therefore equals is antisymmetric. It's also symmetric because if A equals B, then B equals A. So the equal sign is an example of a relation that's both symmetric and antisymmetric. So it is possible. Okay, I don't want these examples to mislead you. Anyway, let's go back and check for other properties. All right, so in this fourth bullet point, we're checking for transitivity. Let's say A over B and B over C are rational. Remember, A, B, and C are real numbers. They're not necessarily rational themselves. Think of the 4 pi, 3 pi example. So if A over B and B over C are elements of the rational numbers, then we can write A over B as M over N and B over C as P over Q. We don't know that this P is the same as this N. We have no way of knowing that in general. And all of these integers are non-zero, as we said. So then let's see. Is A over C rational? That's all we care about. Well, notice we have A over C equals A over B times B over C. Remember, these are all real numbers in the numerators and denominators right now. But now we're going to express in terms of integers. So we have integer over integer times integer over integer. Nothing is zero anywhere, which means we actually have a rational number. We have integer over integer. So that tells us t is in fact transitive. And this relation is reflexive, symmetric, and transitive. We're going to learn in a later section that relations with these three properties are special in a different way. So here's another one for you to practice. We like relations that involve things like A divides B, or A minus B mod 2 is equal to 0, and stuff like that. Let's consider the relation T on N. Remember, in this class, N is the set of natural numbers which does not include 0 in this class. So A is related to B if and only if A divides B. It's important to remember that we're not including 0 here when you're checking these properties. So go ahead, give that a try, pause the video, and rejoin us. Slightly different example. Now our relation is defined on the set of non-zero integers. In other words, we have some negatives and positives here, and this relation U is defined as A is related to B if and only if A divides B. So it's very similar to the previous hands-on exercise. And you're checking whether this is reflexive, irreflexive, symmetric, antisymmetric, or transitive. And when you're done with that, compare with what you got in the previous hands-on exercise. See if there's any connections you notice. Okay. Let's take another one involving divides. Now we're just defining this on the actual full set of integers, which includes 0. So the relation U is described as A is related to B if and only if 5 divides the sum of A and B. So why is this not reflexive? Well, if I take a particular element, let's say 1, and I consider is 1, 1 in the relation U? And the answer is no, because 1 plus 1 is 2, and 5 does not divide 2. So that means the relation cannot be reflexive. What about irreflexive? Well, again, we're asking now the question, is A comma A not in U for all A in A? And this is also not the case because, for example, if you pick 10 for A, 10 comma 10 is in the relation. So the answer to this one is no, because 10 comma 10 is in the relation. Because 5 divides 20. 20 is 10 plus 10. Next, we're going to check for symmetric. So we're going to assume A comma B is in the relation. In other words, we're going to assume 5 divides A plus B. But notice A plus B and B plus A are exactly the same thing, which tells us 5 also divides B plus A. So that means that we're saying if A comma B is in the relation, then B comma A is in the relation. That is going to always be true based on this argument. So therefore, U is symmetric. What about antisymmetric? Well, 2 comma 3 is in the relation, and 3 comma 2 is in the relation, but 2 is not equal to 3. Let me write that over here. So 2 comma 3 is in the relation U, and 3 comma 2 is in the relation U, but that does not imply that 2 equals 3, because 2 equals 3 is not true. So that means U is not antisymmetric. It's not transitive either. So let's consider 1, 4 and 4, 6. Okay, so what we're saying is 1, 4 is in U, and 4, 6 is also in U, but 1, 6 is not in U. In other words, this part of the definition is not satisfied. So what we have is the only property U has is that it's symmetric. Let's say we have the set consisting of just 0 and 1, and we define a relation on this set as consisting of the ordered pairs 0, 0, and 1, 1. Well, that's definitely reflexive, because for every element of A, we have A comma A in the relation. That automatically tells us it's not irreflexive. What about symmetric? Because AB being in the relation automatically means that BA is in the relation. If I switch 0 with 0, that ordered pair is still technically in the set. Same with 1, 1. In fact, if AB is an element of V, then we have to have A is equal to B. So that tells us V is also antisymmetric. And then for transitive, we can think of it the same way. 0, 0 and 0, 0 are in the set, therefore 0, 0 is in the set. Similarly with 1, 1. It's kind of silly to repeat the same numbers over and over, but it's important to think about which number, which 0 fulfills which part of the definition. So for practice, consider the relation where two people, A and B, are related to each other if they have the same last name. So hopefully you have some intuitive idea of whether these three apply before you go into the formal definitions. So think about that and then give it a try with the formal definition for all, checking for all 5 of these properties, whether this relation has them or not. All right. Similar to the last name one, let's say we have a non-empty set of individuals in a community, and we have the relation A is related to B if and only if A is a child of B. You can't be a child of yourself, so that means A comma A, no ordered pair of the form A comma A will be in this relation. That tells us W cannot be reflexive. So that actually tells us that it is irreflexive, because every ordered pair is going to consist of two distinct elements. That's another way to think of irreflexive. If A is a child of B, then is B a child of A? Definitely not. So W cannot be symmetric. Now let's look at the definition of antisymmetric and try to apply it to W. So what that would say is, if A is a child of B and B is a child of A, then A equals B. Well, the question is this if-then statement true? Well, remember what we said. An implication is true if either you have true implies true, or you have false implies whatever. Okay? A is a child of B and B is a child of A is never going to be true, because it has to be one or the other or neither. They cannot both be true at the same time. That means the premise of this implication is false, which says that this entire implication is in fact true. So that means W is antisymmetric. So again, remember that it is possible for relations to be symmetric and antisymmetric. We talked about the equals relation as an example of that. And it's also possible for a relation to be neither symmetric nor antisymmetric. So that might be a good thing to explore and come up with on your own by choosing some ordered pairs to make that work. If you're not convinced yet that this relation is antisymmetric, let's look at it in a different way. Remember, the contrapositive of the definition says that when A is not equal to B, there's three possibilities. Either A is not related to B and B is not related to A, or if A and B are related, then you either have that A is related to B but B is not related to A, or B is related to A but A is not related to B. Remember, related means in terms of the relation being described. And then transitive definitely is not going to work. So if A is a child of B and B is a child of C, does that mean A is a child of C? No, A is the grandchild of C. So that's not what the relation is about. So W is not transitive. Therefore, what we have is the relation is irreflexive and antisymmetric.